Good day, everyone. We're reviewing Wetzel's Limnology textbook. This is edition number 4, and we are starting on chapter 12 today, Salinity and Ionic Composition of Inland Waters, with Hilary A. Duggan, with the Center of Limnology at the University of Wisconsin in Madison, Wisconsin. Salinity refers to the mass of dissolved inorganic solids found in water, and is important in limnology both for its influence on water density and therefore water movements, and for the individual constituents the term encompasses. Owing to the power of water as a solvent, salinity comprises numerous ions and molecules, but for most limnological purposes, salinity is considered the mass fraction or mass concentration of the major cations, which are sodium, magnesium, calcium, and potassium, and anions, chloride and sulfates, and carbonate species, bicarbonate and carbonates, dissolved in water. When high precision measurements is required, the small fraction of mass contributed by silica, minor ions, and nutrients may be important. Salinity is often considered interchangeable with total dissolved solids, but TDS includes the mass of dissolved organic matter, or DOM. This subtle difference is often significant but becomes important where DOM concentrations are high, as DOM can affect density. In physical oceanography, the definition of salinity has a long history driven by its important influence on water density and ocean mixing. Approximating salinity became necessary because comprehensively measuring the complex mixture of constituents in water was, and still is, a massive undertaking. The term salinity was originally proposed after quantitative analysis revealed that of the numerous elements dissolved in ocean water, only water and salts were of consequence to the overall mass. Because salinity is dominated by ionic constituents that are positively and negatively charged, salinity can be approximated by electrical conductivity, EC, a measure of a solution's ability to conduct electrical flow, expressed in micro or millisiemens per centimeter. Older literature often used the unit micro-MOs or micromos, which is equivalent to microsiemens per centimeter. But the former term is now considered obsolete. By definition, EC is the reciprocal of the resistance of a solution measured between two electrodes 1 centimeter squared in area and 1 centimeter apart. In fresh to saline waters, the resistance of water to electron flow declines with increasing ion content. Hence, the purer that water is, that is, the lower its salinity, the greater its resistance and the lower the EC. EC is also highly temperature dependent. Temperature increases from 0 to 30 degrees C, both decrease water viscosity and increases the solubility of most salt, increasing EC about 1.9% per degree Celsius. Thus, specific conductance is often referred as EC, corrected to 25 degrees C. So before moving on, let's look at table 12-1, properties related to the ionic composition of inland waters. So salinity. So the common SI unit, or international system unit, or Système International, is milligrams per kilogram or milligrams per liter. And the definition is the mass of dissolved inorganic solids in water. Total dissolved solids, milligrams per kilogram or milligrams per liter, is the mass of dissolved solids in water, including dissolved organic matter, or DOM. Electrical conductance in microsiemens, ability of water to conduct an electrical current. So therefore, as we just read, pure water has a lot of resistance. However, if you add salt to the water, that will decrease the resistance and it will increase the ability of the water to conduct electricity. Electrical conductivity in microsiemens per centimeter. Electrical conductance normalized to a unit of length per cross-sectional area. And then specific conductance in microsiemens per centimeter, the same unit and above, but at 25 degrees centigrade. So that is normalized to that temperature. Electrical conductivity of 1 cubic centimeter of solution at 25 degrees C. Note, dissolved gases also influence water density, but are not typically accounted for in measurements of TDS or salinity. Table 12-2. So salinity and ionic concentration in milligrams per liter of Swedish bicarbonate freshwaters in relation to specific conductance. And then in this case, the specific conductance is at 20 degrees C instead of 25, and it's in microsiemens per centimeter. So here what we're looking at is, what we're seeing is like, as you increase the salinity, you also increase the specific conductance. And because you enable the water to conduct more electricity, because the salt are getting used to conduct the electricity, because they are ions that are polar in the water, like that are either negatively or positively charged, and that facilitates the transport of electrons through the solution. So here, for a salinity of 10.5, here are the concentration of the different ions, and so you can see that the ions increase in concentration as the salinity increase, as well as the specific conductance. So the relationship between EC, so let's, before that, what is said in this little footnote here. In this chapter, data are presented in their original measurement units. Since the density of pure water is 1 kilogram per liter, concentration units present as mass per mass or mass per volume are often considered equal for fresh water. This is not true for saline waters. The relationship between EC and salinity and density is dependent on the relative proportion of dissolved ions, as ions are not equal in their influence on conductance. And therefore, the relationship of EC to salinity is site-specific and only holds for a constant relative ratio of dissolved ions. The homogeneity of the composition of sea salt led to the use of practical salinity scale in oceanography in the 1980s, a unitless scale defined as a conductivity ratio. Similar EC to salinity or EC to density relationship can be devised for inland waters where the proportion of the individual ions are relatively constant. However, as noted, EC only reflects ionic species and overlooks neutral species such as dissolved silica, which can present in high concentration in some inland waters. Due to this limitation and other thermodynamic consideration, oceanographers have since adopted the term absolute salinity, which is a true measure of total dissolved inorganic solids. Limnologists rarely have the luxury of working in a homogeneous setting and must be cognizant that relative proportion of dissolved ions are typically in flux. The specific conductance of the common bicarbonate type of lake and river water is closely proportional to concentration of the major ions. Once the specific conductance and concentration of the major ions are known, changes in specific conductance reflect proportional changes in ionic concentrations. This relationship is not true, however, for minor constituents of lake water, for example, nitrogen, iron, manganese, strontium, or especially phosphorus, as a large change in relative concentration may have an indistinguishable effect on specific conductance. As would be anticipated, a positive correlation exists between specific conductance and pH in the intermediate pH range of bicarbonate freshwaters, but this relationship deteriorates among lakes of low salinity and high DOM content. Whether or not to report EC, specific conductance, salinity, or TDS will depend on the application, and a detailed description of the method used to calculate this value should be provided. Salinity and ionic composition of inland waters. The beauty of inland waters is in their diversity, and salinity is no exception. Lakes range in salinity from almost pure water to the record-setting Gaitale pond in Ethiopia with a TDS of 433 gram per kilogram, 12 times the concentration of seawater. Given the natural gradient of salinities in inland waters, it is useful to differentiate fresh water from saline water, even though there is no ecological basis for such an exact threshold, and opinions on terminology have varied through time. Nevertheless, for practical purposes, the boundary between fresh and saline water has been generally accepted as 3 grams per kilograms, as originally put forth by Williams. For some application, more regionally meaningful thresholds may be appropriate, and suggestions have included 0.5, 1, and 5 grams per kilogram. For instance, 99% of Canadian lakes are less than 3 grams per kilogram, as compared to only 50% of Australian lakes. Freshwater for drinking purposes is often restricted to TDS less than 0.5 grams per liter for aesthetic effects. So meaning by that for like beauty-based effect rather than health effects. Lake with salinities greater than 3 grams per kilograms are referred to as saline lakes and further differentiated into those of marine origin and maybe brackish salinity ranging from the freshwater cutoff up to ocean salinity of 30 to 35 grams per kilogram, and those of non-marine origin termed athalasic lakes. The water, so Lhasa is sea, so something that doesn't come from the sea. The water in saline lakes is referred to as brine, meaning a salty solution. Notably, many of the largest lakes on Earth are saline, including the Caspian Sea, the Issyk-Kul Lake, Lake Van, and Lake Turkana. But the majority of the hundreds of millions of lakes on Earth are freshwater lakes. A more exhaustive classification system of athalasic saline waters includes freshwater less than 0.5 grams per liter, subsaline between 0.5 and 3 grams per liter, hyposaline between 3 and 20 grams per liter, mesosaline between 20 and 50 grams per liter, and hypersaline greater than 50 grams. Well-known hyposaline lakes include the Great Salt Lake, the Dead Sea, and Don Juan Pond in Antarctica. Lastly, poikiloalin is a term used to refer to water of variable salinity. Detailed summaries of inland saline waters have been made in several studies and are discussed in section 3. The ionic composition of freshwaters is dominated by dilute solutions of alkali, sodium and potassium, and alkaline earth compounds, calcium and magnesium, particularly bicarbonate, carbonates, sulfates, and chlorides. The concentration of 4 major cations, calcium, magnesium, sodium, and potassium, and 4 major anions, bicarbonate, carbonate, sulfate, and chloride, usually constitute the total salinity of the water for all practical purposes. Major ion composition of inland waters is commonly expressed in mass concentration, or milligrams per liter, or micrograms per liter, or molar equivalent, MEQ per liter, or microEQ per liter. The latter allowing a check of ionic balances where the sum of cations in milliequivalents per liter is equal to the sum of anions in milliequivalent per liter. Because the conversion between mass and molar equivalent changes ionic ratios, the choice of units must be clearly stated. So before moving on, let's look at these figures here. So this is the A is the Gibbs diagram, or also known as the boomerang diagram. And it's a conceptual representation of the processes controlling the ionic chemistry of inland surface waters. So on the x-axis you have, we have a calcium, it is calcium bicarbonate dominated, and this is sodium chloride dominated. And then on the y-axis we have the salinity in milligrams per liter. And then here we have rainfall runoff, so high and then low. And so that's where we are at in terms of the interpretation of this graph. So why boomerang? Because there's there's a sort of shape that looks like a boomerang here. So inland, coastal, and so dominated by calcium bicarbonate, and dominated by sodium chloride, as I just said. Atmospheric precipitation dominance, so on the right side. So therefore, with low salinity waters, that is dominated by sodium chloride. We have it's most of the origin of that type of sodium chloride is from atmospheric deposition. But then in the opposite, we have rock dominance, where the salt are coming in from the rock for the erosion of the rocks. And then evaporation, transpiration, so where we don't have a lot of precipitation because we're in a low precipitation realm there, and we're on high salinity, is dominated by evaporation. Evaporation is a strong driver of the salinity there. This is another diagram. This is the total dissolved solids on the y-axis, and on the x-axis we have the ratio of sodium to calcium and sodium ions. And so prevalence of sodium in relationship of calcium versus TDS of the James Glory database of major world rivers, as well as 10 saline lakes. Large circles represent the world weighted average, orange, and world spatial median, red. So the orange is the world weighted average, and then the red is the world spatial median of global rivers. So this is only for rivers. Prevalent, although there are some like seas, there are large lakes. So here what we see is so for high dissolved, total dissolved solids, a lot of the large lakes, saline lakes in the world, are dominated by the sodium to calcium sodium ratio. So are pretty much dominated by sodium based, and to some extent calcium. So for example, Great Salt Lake, Salton Sea, Mono Lake, Caspian Sea, and the likes. Now we also have some lakes here that have high total dissolved solids or high salinity, but it's the inverse, where the ratio of the sodium to calcium to sodium is low, and close to zero in this case. And then here are all the water samples, and kind of shows you the distribution of that. So what you can do is you can superimpose this diagram, on the Gibbs diagram, and you can see that a lot of these lakes, or rivers I should say, that have salinity, that are saline, is due to the erosion of the rocks, contributed to the salt. And then C, prevalence of sodium in relationship to calcium versus specific conductance of 1,230 lakes and 2,261 rivers. So the rivers are squares, and then the lakes are circles. So it's kind of difficult to distinguish between the two, but the squares are gray, and as they were saying, the squares are rivers, and then the little dots are darker gray, or are kind of a bluish gray, and that would be the lakes. And so what we see here, this is specific conductance on the y-axis, sodium to calcium sodium ratio, so the same ratio that we're dealing with here. They didn't overlay the boomerang there, but we can kind of guess it. So a lot of the lakes' salinity is once again driven by rock rather than other processes such as evaporation, transpiration, precipitation, atmospheric precipitation dominance, and the likes, which would be in the lower part of the diagram if that was the case. And and then on the other end of the spectrum, where we have sodium dominated base waters, which correspond to those seas, here we have like a pretty good distribution between the rivers and the lakes. So it doesn't look like there's a specific type that dominates there per se. But you do have in some instances some let's see, the squares are, I believe, let's see here, the squares are the rivers. We have some squares with some rivers with a pretty high salinity, and we have a few lakes like that as well. Okay. And then this is figure 12-2, total dissolved solids of the world major rivers. And A. So therefore, you can see like, yeah, I mean, this is like an exponential curve actually. It doesn't really like, it's not a linear curve. That means that we have like, the rate is not constant and consistent. And so at the end of that spectrum where we have high TDS for some of the rivers, you know, you have very high, like you have TDS greater than 2,000 for some rivers. And it's really not clear, you know, in terms of density, how many rivers do we have in that. Here they put in, I think the dashed line represents the mean global river TDS of 128. So this is the mean is here. And so for example, the Danube, which is a river, of course, some pretty high salinities, has salinities in the 500. So a lot of rivers are actually, at the end of the day, for aesthetic purposes, you probably can drink the water from most of the rivers, even the Mississippi, if it was not contaminated in some areas. B, ratios of bicarbonate to total ions and calcium. Total ion for the same rivers. So let's see here. We have bicarbonate to total mass of ions, and then calcium to total mass of cations. And so here we are seeing like calcium-dominated rivers here, which would be in caustic basin. And then we have bicarbonate to total mass and ions. So, for example, like the Mekong and the Amazon and the Danube, they are rivers where the bicarbonate is overall dominating the river's ionic composition. And then you have some rivers that are in kind of in the middle ground, such as, for example, the Mississippi, or to some extent the St. Lawrence and the likes. All right, so I think it's going to be it for today, and well, maybe why don't I read this, and then we'll start tomorrow at control mechanism and salinity. It is commonplace for fresh waters to be characterized as soft water if waters are dilute and ions are derived from the drainage of acidic igneous rocks. In contrast, hard water contains high concentration of calcium Ca2+ and magnesium 2+, usually derived from the drainage of calcareous deposits. The amount of salicylic acid which occur largely in undissociated form are usually small but occasionally significant. Concentration of ionized components of other elements such as nitrogen, phosphorus, and iron, and numerous minor elements are of immense biological importance, but are minor contributors to total salinity. So I think that's it for today, and tomorrow we'll pick it up at control mechanism and salinity. Thank you, and I'll see you tomorrow. Bye.